Good morning. Today we're going to look at derivatives of trig functions. Trig functions pop up all over the sciences, especially in, say, physics classes or any class that you're looking at waves. So they're important to understand. Before we dive into trig functions in terms of their derivatives, let's do a brief review of trig. So first off, what we're going to study today is sine of x, study cosine of x, and we'll study tangent of x. So trig functions are all based on the unit circle centered at the origin. And basically, whatever value you put in here is going to be the radian measure as we move around the circle counterclockwise if that input is positive, and clockwise if that input is negative. The sine will spit out the y value, or the y coordinate of where we are on the circle. Cosine will spit out the x coordinate, and tangent will spit out the ratio of the y and x coordinates. So with that in mind, let's see if we can sketch the sine function by reminding ourselves of the unit circle. So sine of 0 is, again, we're moving 0 radians, and we're looking at the y coordinate there. Well, the y coordinate there is just 0. So for the sine function, that graph will go through 0, 0. Let's move this way, a quarter of the way around the circle. So in radian measure, that's pi over 2. Pi is the same thing as 180 degrees. So as I move this way, again, the sine function spits out the y coordinate. So when we're at pi over 2, the y coordinate is 1 on the unit circle. Keep moving further. The y coordinate at pi radians is just 0. Next, we're at 3 pi over 2 radians. 3 pi over 2. And it looks like the y coordinate is negative 1. Finally, 2 pi, we're back home to 0. So I can just connect the dots, and boom, there's my sine curve. The process repeats over and over again. Sine is what's known as a periodic function. It's got a cyclic nature to it. Okay, so again, the sine function then, all it's doing is it's spitting out the y coordinates as I move around that unit circle. The cosine function spits out the x coordinates. So I'm going to put the same values, pi over 2 pi, 3 pi over 2, and 2 pi. So once you pause the video, see if you can play the same game, move around the unit circle, and plot points knowing that cosine is spitting out x coordinates. So hopefully you give that a shot. Cosine of 0 is going to be 1 because that's what the x coordinate is there. Cosine of pi over 2 is going to be 0 because the x coordinate at that point on the circle is 0. Cosine of pi is negative 1 because that's where we are in the circle. Cosine of 3 pi over 2 is 0. And cosine of 2 pi, we're back to the start, and the x coordinate there is 1. So let me fill in that picture. So this is cosine of x. So I'm not going to graph tangent of x. We don't actually need it for what we're doing. But just know, again, that tangent is sine over cosine. This guy's going to have asymptotes wherever cosine happens to be 0. Just as an FYI. Okay, so this is some information that we're actually going to need for today. And let me actually break this off over here. Let's make this side of the board my trig notes from pre-calc, and we'll do the calculus on that side. So if you look at this picture, let me extend this a little bit. I'm not going to prove this, but if you look at the picture, when x is close to 0, sine of x is approximately equal to what? Well, if I draw the line y equals x, we can see that it pretty much maps right to the sine function. So if x is close to 0, sine of x is approximately equal to x. So party trick, tell your friends that you can compute sine of x faster than a calculator. Sine of 0.003, well, that's going to be approximately 0.003. That's what that's saying. Okay, another formula we need from trig that I never remember. I know it exists, but I always forget it. So let me write it down. It's the sine of a sum formula. There's a sine of a sum, cosine of the sum, and differences as well. The sine of the sum formula is sine of a plus b is sine of a times cosine of b plus sine of b times cosine of a. Again, I'm sure you've seen that in pre-calc. We're going to need that in a couple of minutes. What else do we need? Oh, cosine of x. Cosine of x. So this guy over here. Let's see. We can take the cosine and think of it in terms of sine. If I take this picture, and I just shift it this way by pi over 2, move it on over, hopefully you'll see that we're actually going to get this picture. Right? You just move that over by pi over 2. So in other words, if I move the sine graph by pi over 2 to the left, I'll get the cosine graph. Well, if that's the case, then from pre-calc again, our knowledge of transformations, cosine of x should be sine of x plus pi over 2. So if you shift the graph to the left, you're going to add the value inside the argument. Two more things I want us to know. 1 over cosine squared of x. Well, that's the same thing as secant squared of x. Secant squared of x is defined as 1 over cosine of x. And then finally, again, these will be used in our investigation of the derivatives. Finally, we know that sine squared plus cos squared is 1. That's a formula everybody should know. If you don't know it, commit it to memory. It pops up all over the place. So let me quickly show you why this is true, by the way, by looking at a picture. So let's say I drew a triangle like this. Well, the length of this triangle is 1. And let's say the angle that I'm moving in radians, let's say I call that x. So x is the radian measure. Well, if that's the case, then that coordinate should be sine of x times cosine of x. So again, it's a little awkward because I'm using x for the radian measure, but you'll see why in just a second. So I'm moving x radians. This point is cosine of x comma sine of x. Well, if that's true, then I guess this length, which is the x direction, this length should be cosine of x. This length, which is the y direction, should be sine of x. Cosine of x is this length, sine of x is this length, 1 is that length. What dead Greek comes to mind? Hopefully you said Pythagoras. Cosine squared plus sine squared should be 1 squared by the Pythagorean theorem. Boom. So I guess sine squared plus cos squared is 1. Okay, so this is all information that we're going to use in developing our derivatives. So first, let's look at the derivative of sine of x. I'll give you a minute, pause the video, write out the definition of the derivative for this guy. All right, hopefully you said, oh, that's the limit as h goes to 0, sine of x plus h minus sine of x all over h. Okay, so let me look at my toolkit here and pause the video, ask yourself if anything in there looks like anything over here. So hopefully you said, oh, sine of x plus h, that looks like this guy. So I don't know if it's going to help or not, but it's a door that I'm going to open up. So let's see what's inside. We have sine x, cosine h, plus sine h cosine x minus sine of x all over h. So that's where we're at. All right, so at this stage, is there anything that you can do? Is there any algebra you can do on that? Well, again, I don't know if it's going to help or not, but hopefully you said I can factor sine of x out of both those guys. So this is the limit as h goes to 0. Sine of x times cosine of h minus 1 plus, so I just factored out the sine of x, plus cosine of x, sine h, all over h. I just switched the order here because of a future step. It doesn't matter because we're multiplying. Multiplication is commutative, so you're allowed to do that. Okay, what I'm going to do now is I'm going to break that big sum into two pieces. Why am I going to do that? Well, that's worked in the past. I can't see the final solution, but it is something that has worked, so it's something that we would try. So, in other words, I'm going to write this as cos h minus 1 over h times sine of x. That's the first piece. And the second piece is cosine of x times sine h over h. Okay, so we know that the limit of a sum is the sum of the limits as long as both limits exist. And then the limit of the product is the product of the limits as long as both limits exist. It sounds like something from the Wizard of Oz, but anyway. So let's study each of these guys, and let's see if we can come up with their limits, and then just multiply and then add them together. Well, as h goes to 0, sine of x could care less, so that's just sine of x. Times this limit, let me hold off on that, let me just write it like this. As h goes to 0, cosine could care less. And let's look at this guy. Also, let me just rewrite it like this. So I guess in this step, all I'm doing is pulling out the constants. So I want to study those a little bit more in depth. Okay, I want a little bit more room, so this I won't actually need anymore. I don't need this anymore. So let's pick apart those two limits. So let's first look at this guy. Well, hint, this will be helpful. See if you can deduce what that limit is by looking at that expression. So pause the video and give it a shot. Well, hopefully you said sine of x is approximately x if x is close to 0. So sine of h is approximately h when h is close to 0. Sine of h over h is then going to be approximately 1 for small h. Therefore, as h goes to 0, that limit is going to be 1. So this is cosine of x times 1. Okay, let's take a look at the other piece. The limit as h goes to 0, cosine of h minus 1 all over h. Well, it turns out that this is actually the definition of the derivative at a particular point for a particular function. Pause the video and see if you can figure out for which function, at which point, is this illustrating the definition of the derivative. Hopefully you gave that a shot and you said, well, if a is 0 and f of x is cosine of x, then f prime of 0 is the limit as h goes to 0. Cosine of, let's see, 0 plus h, a plus h, minus cosine of a, cosine of 0 over h. But cosine of 0, if you look at that graph, which I just got rid of, cosine of 0 is just 1. Cosine of 0 plus h is cosine of h. So this is the same thing as cosine of h minus 1 over h. So this expression is f prime of 0. Well, you might say to yourself, well, I'm not going to be able to compute that because I don't know the derivative of cosine of x. You're right, you don't know the derivative of cosine of x. But look at your graph and determine, just by looking at it, what the derivative of cosine is at 0. Well, hopefully you said, oh, the derivative there is 0 because it's got a horizontal tangent line there. The derivative of cosine is 0 at 0. Fantastic. So now this becomes cosine of x because that first piece disappears. There's something poetic about this. The derivative of sine of x is cosine of x. Beautiful. Okay, so up until now we've used the definition of the derivative to find derivatives. Well, for the next two derivatives, and actually in next lecture as well, we're going to use other techniques than the definition of the derivative. What do I mean by that? Well, if I want the derivative of cosine of x, that's the same thing as the derivative of sine of x plus pi over 2. And we can compute this derivative using the chain rule. The derivative of sine of stuff is cosine of stuff. Cosine of stuff times the derivative of that stuff. So times 1. So this is a true statement, but this is not how we typically write the derivative. In fact, I've never seen anybody write it like this. There's something elegant about this. Let's see if we can somehow convert this into something having to do with sine. So let me erase this. I guess I do need my graphs. And I'll quickly reconstruct them. So sine is like that. So this is pi over 2. And cosine is going to be like this. Okay, so this is pi over 2 pi. If I take the cosine graph, and I shift it, if I shift it to the left by pi over 2, and I'm going to give you a minute, pause the video, see if you can then re-express cosine of x plus pi over 2 in terms of sine somehow. Well, hopefully you paused it and you said, oh, if I move this guy over by pi over 2, if I move it this way, then it's going to be something like this. And if you look at the sine graph, it's just going to be the opposite of the sine graph. It's going to be the opposite. So this is the same thing as negative sine of x. A little bit surprising, as far as I'm concerned. I would have thought that if the derivative of sine of x is cosine of x, then the derivative of cosine of x is sine of x. But that's not the case. The derivative of cosine of x is negative sine of x. Finally, to compute the derivative of tangent, we're just going to recognize that this is the derivative of sine over cosine. We can then employ the quotient rule. So I invite you to pause the video, see if you can derive the derivative of tangent. I'll even let you know that you're going to use this formula. You use this formula in that process. So give that a shot. Well, hopefully you said that's bottom times the derivative of the top, derivative of sine is cosine, minus top times the derivative of the bottom. The derivative of cosine is negative sine all over the bottom, quantity squared. Quick note about this before I continue with this. I don't want to forget this. So you could have written it like this. Typically, when I do problems involving calculus, typically what I do is I use this notation. I just feel like it's a lot cleaner and just more compact. So you could write it like this, but I'm going to be writing it like this. Okay, so anyway, in that notation, we have cos squared plus sine squared on top. And cos squared plus sine squared, by what we have over here, is just 1. And 1 over cosine squared is secant squared. Who would have thought that the slopes of my tangent function can be determined by looking at the secant squared function? Never would have thought that in a million years. So in summary, we have that the derivative of tangent is secant squared of x. All right, in this lecture, we looked at the derivative of sine, which is cosine, derivative of cosine, which is negative sine, and the derivative of tangent, which is secant squared of x. We also saw a new way that we could come up with derivative shortcuts, which is not using the definition of the derivative, but using some other tools that we have at our disposal. So what we did today is we used composition as a technique, and we also used the quotient rule as a technique to come up with derivatives. So that's all I have to say for today. Hope you enjoyed the lecture, and I will see you next time.